Hi, this is Mr. Yeager, and today we are looking at simple harmonic motion, and we're going to start off with pendulum. So this is an introduction to some of the terms and what is simple harmonic motion, and then we're going to look at one type of simple harmonic motion, and that involves pendulums itself. Then you'll see in a later video, we're going to look at springs. So, for simple harmonic motion, all right, simple harmonic motion, or SHM, all right, it means a repeating occurrence over and over again, a repeating pattern of motion, all right? One that's not going to really change that much, but it's just a back and forth, to and fro motion. That's our classic one. So this is going to obviously relate to waves as well. If you just think of ocean waves, that's basically simple harmonic motion of the constant coming of ocean waves. In oscillation itself, if I go to the first real definition, you'll often see how many oscillations are occurring. An oscillation is one complete motion, one complete wave motion. Now again, be aware that this is a term in simple harmonic motion. There are a lot of different terms used to say a repeating pattern. It can be waves, it can be oscillations, it can be pulses, it can be anything that's just happening over and over and over again. So really quickly, I want to take you to a website called PhET. Okay, you can see it at the top there, all right, phet.colorado.edu. And all this is trying to show you is, hey, this is oscillating motion. You can see the springs bouncing with these masses on them back up and down, up and down. And so this would be oscillating motion going on the whole time, all right? If I do slow it down a little bit, okay, we could go ahead and start counting oscillations. So usually I would start counting oscillation obviously from either the top or the bottom. So if I'm looking at the gold one here, I would say, all right, here we go. That is one oscillation, two oscillations, and so forth, okay? One complete up and down motion is one oscillation that occurs, and it's obviously going to keep going. It's a repeating pattern, okay? Obviously, one mistake that you do not want to do is I do see students who do this. When I say count the oscillations, they'll go 1, 2, 3, 4. That's not, what are they counting? They're counting a half an oscillation, and that's not correct, okay? If I show you just one other one, obviously the ones we're going to get into quite a bit, all right? The pendulum's the same way, okay? Pendulum, again, out of PhET, okay? I want to make sure I recognize that website, all right? Out of PhET, this is a pendulum, obviously oscillating back and forth, okay? Obviously, we will be looking at a situation where there's no friction involved, because if there was friction, even though it will continue to oscillate in a repeating pattern, it's going to obviously swing less and less over time. But this one's obviously repeating the exact same amount. So energy, as we're going to see, will be conserved. It might just alter from one form to another. But same thing with pendulums. When we count oscillations, it would be 1, 2, okay, and so forth, okay? And so that would be one thing that we, again, if you do a lab with pendulums, you make sure to count this correctly so you don't make a silly mistake when you're trying to do some of the math later on. All right, thank you, PhET. So, oscillation is one term for simple harmonic motion. These two are probably the main two terms and measurements we're going to do. It's period and frequency. Period and frequency. Okay? And so you can see period, which we're going to denote capital T. All right? We talked about period before a little bit in circular motion. It's the same thing. It's the time it's taking for one complete oscillation. In circular motion, it was for one complete rotation, returning back to where you started. So, again, period is time over oscillations. Okay? The time for one oscillation, it is measured in seconds. There is no unit for oscillation, so it's time for however many times something occurs. So it's just make sure that we understand that time will be on top there. Okay? Frequency, which we're going to denote F, we haven't really talked about frequency yet. Denote F is the number of oscillations over time. So hey, what does this say about period and frequency? They're inverses of each other. The frequency equals the inverse of the period. All right, basically it's just inverted. Obviously, period will equal the frequency inverted, okay? If we invert one, we got to invert the other, okay, depending on the situation we're going to. So if you have one, you have the other. If you know frequency, you know the period. You just got to make sure, obviously, that you don't get them backwards, which a lot of people do. But again, you can see how I wrote this out. Oscillations over time. This could be waves, pulses, rotations over time, okay? How many, again, simple harmonic motion, whatever it is, oscillations you're doing, that's what we repeat. The thing is, as I stated, there is no unit for oscillations. It is just a number, okay? It is just a number. So we usually will just say frequency is 1 over time. 1 what? 1 anything, okay? 1 pattern that's occurring over and over again. So we actually have a special unit for this, okay? We could say frequency equals 1 over seconds. Okay, that's not really that special. It's just writing it out as it's stated there. 1 over time, 1 over seconds. But this is known as a hertz. Hz. A hertz. That is the unit for frequency. That is telling you how many times something is occurring over 1 second. Okay, it's always over 1 second. And the last way we can sometimes write this is seconds to the negative 1. All right. So you can see this all any way. So we could say, I'm going to write it up here, the frequency of a wave is 10 hertz. What does that mean? That means there's 10 waves passing in 1 second. But I could also write it like this, 10 seconds to the negative 1. They're all the same thing, okay? So please don't be confused by any of those. Obviously, the main unit to learn is hertz, okay? So period and frequency, they're going to be very important. I like to mention amplitude, okay? Amplitude. It is the height of the wave from equilibrium. That's the key, though, from equilibrium, okay? The maximum distance from the starting point, all right? Since this is height, it is measured in meters, centimeters, whatever, obviously a distance unit, all right? It will be related to essentially the energy of the wave itself, all right? How intense the wave is. Obviously, a larger wave will usually carry more energy with it. So there is an energy component involved with amplitude, but there's no calculation. We just have to know what it is. We have to identify it on a graph, on if I give you a wave diagram, you have to sit here and go, all right, here's the equilibrium. This is equilibrium, this is equilibrium, this is equilibrium, this is equilibrium. One amplitude is the amplitude from the equilibrium all the way up to the top, or the depth of the wave. It doesn't matter. They're the same thing. We don't do waves that are different amplitudes from their crest and their trough. Again, crest being the top of the wave, trough being the bottom of the wave. Okay? They're going to be equal on both sides. I've never seen one where they don't come out equal on both sides. Okay? Good. I mean, that's it. Usually the only mistake some people will do is they'll tell me the amplitude is 4 meters, but obviously based on this one, you can see what they do. They measure from the bottom to the very top of the wave. That is incorrect. Incorrect. All right, so that leads us to pendulums. Okay? In this unit, we basically are looking at pendulums, and we're going to look at springs in terms of their forms of simple harmonic motion, and then we do a completely separate unit on waves. All right, so with pendulums, there's not too much we have to worry about. We're mainly interested in going, what could change the period of the wave? When we do simple harmonic motion, we're going to be interested in the period. What can you do to alter the period of the wave? And so, with pendulums, there's a lot of different things that we could alter on that pendulum, okay? If I go back to this, what could I change about this pendulum, okay? And I can change the mass that's hanging off the bottom of it. I can change the length of the string, and I can change for how high I start from where I drop it. Obviously, I pull this up higher, okay? If I pull this up higher, I don't know if I can grab it or not. Grab it. If I pull it up higher, this would be called the amplitude. Okay, obviously it's now able to swing even higher. Okay, the thing is though, we're interested in period. Okay, period. How long is it taking to complete one oscillation back and forth? So those are the 3 things that you could actually change physically: mass, amplitude or release point, and the length of the string. Now there is another factor, but obviously you cannot change it. Don't worry about the amplitude being squared out. You cannot alter, obviously, the gravity But it's definitely affecting a pendulum. I mean, what's going to make the pendulum fall and start going down? Following a circular motion pattern, because that's what it's doing. It is following circular motion. Okay? And so these are our four factors. So we say these are the things that could change the period. I'm not saying that they will change the period. All right? And this is what obviously you're going to confirm in a lab later on. I'm going to obviously go through what will, and then you're going to confirm it during the lab with obviously a little bit of error. Okay? So what will change the amplitude? Okay? I'm going to jump right into it. I'm basically going to give it to you here. One is the length. The length of the string will change the amplitude. Okay? The length will change the, not the amplitude, sorry. Length will change the period. Okay? And so what do we have to think about here? All right, if I draw out two pendulums, all right, let's say they both are brought up to the same angle, so basically the same amplitude, okay, same amplitude start, and they both have the same mass at the bottom, so everything's staying constant. Which one will complete an oscillation faster? All right, and you can pretty much guess based on my drawing here. If I decrease the length, all right, if I decrease the length, I'm going to decrease the period, which means, again, this is where people get confused, it's faster. Smaller period means less time to complete the oscillation. Okay? Less time to complete the oscillation. And that means you're going to have a higher frequency. Again, period and frequency are inversely related, but we see that length and period are going to be directly related. All right? If I increase one, I'm going to increase the other. And again, smaller period means faster. Faster. So don't get confused there. Some people go, you know, greater length is going to go faster. No, 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 no. It's going to go slower. Okay? So you got to be careful there. So obviously the reason is we have to justify this. Why is length going to decrease the period? All right? Well, we can just see it here. What do you notice? All right? What's the distance that pendulum A has to cover versus pendulum B? Which one has to cover a smaller distance to complete an entire period? The answer is A. All right? And so basically we could say if you decrease length, it's going to go faster because it has a shorter distance to cover. That's all we have to say. All right? It's not like one's going to be accelerated by gravity any more than the other. They're both going to be accelerated the same. It's just, hey, this one doesn't have to travel as far. Okay? It doesn't have to travel nearly as far. Okay? So that's what we are looking at here. Sometimes people talk about the arc distance. The arc distance. Okay, it has smaller arc distance. So that's it. That's what you need to know about length. Now, it turns out there's only one other factor that will affect it, and that is gravity. All right? And again, unfortunately, well, hopefully not unfortunately, we cannot control the gravity at all, so that's something we're not going to mess with. But if I go to another planet, which obviously we like these theoretical problems, how would the pendulum swing? Okay? And so we can obviously think about this. If I increase gravity, what's that going to do for the pendulum? Well, that's going to increase its acceleration, meaning it's going to go faster, which means what's that going to do to the period? It's going to decrease the period. So increase gravity means faster pendulum, decrease period, increase frequency. So while length is directly related, gravity is inversely related. I want more gravity. More gravity, more acceleration. Okay? Pendulum will have a greater velocity. All right? So those are the two that will affect it most. So if I go to the moon, gravity decreases. This pendulum should take longer to swing back and forth. It's not going to be as quick. Okay? So that's gravity. Okay? As for the period of a pendulum, so now we can develop this formula. And here's your formula for a pendulum. It's the only formula we use for a pendulum. The period of a pendulum will equal 2 pi. We have that in there because it's following an arc. It's following a circular path. All right, times the square root of length over gravity. Length over the acceleration due to gravity. This is your formula. So you can see based on the formula, the only two factors involved are length and gravity. And so therefore, you can see length is on top because if I increase the length, I'm going to increase the period. They're directly related. But if I, if I increase, messing things up. If I increase the gravity, that means this number will get smaller. Okay, if I increase the gravity, this factor over here will get smaller, the square root will get smaller. That means I'll have less period. Okay, it'll go faster. So that is mainly your big equation involved in pendulums. So real fast, why don't mass and amplitude affect it? Okay, why does mass not affect the period? Okay, and it all has to do with the fact of, if I have a 1 kilogram mass and I have a 2 kilogram mass, if there's no air resistance, no friction, which one's going to be accelerated faster? And the answer is neither. Okay? Mass doesn't affect because gravity accelerates all objects the same. Again, we will only do these without any resistance, without any friction. But gravity accelerates all objects the same. So if you ever have to explain why did it not change the period when I put a 10 kilogram mass on there, it's because gravity accelerates that just as quickly as a 1 kilogram mass. Again, you have to keep all the other factors constant. You've got to have controls. So all three other factors have to be kept the same. You have to still release from the same height, and we should still obviously have the same length. Okay, these should be the same length strings. Is what obviously I'm trying to show there. Okay, so that is mass. What about amplitude though? What about amplitude? Okay, or release point. What if I release a pendulum from very low, so it only has to go so far and back, versus 90 degrees, which everybody loves to do. I want to release it from 90 degrees and make it go all the way down and around to the other side. All right. Why would amplitude not affect the period? Well, let's think about it. Okay. Both objects are going to be accelerated by what? They're going to still be accelerated by gravity. Okay. They're going to still be accelerated by gravity. All right. And so you can sit here and go, okay, which one's going to go faster? Clearly, this one's going to have a higher velocity. The one on the right, the 90 degree where I pull it all the way up. It will have a higher velocity than A. I'm going to write pendulum A and B. B will have a higher velocity. But what does B have to do? It also has a much farther distance to cover. And it turns out both of these basically cancel each other out in regard to the period. They basically cancel. They go, all right, sure, you're going faster, but you have more distance to cover. This one right here, definitely going slower, but it only has a small distance. Okay, so it turns out that ratio of basically d over v equals period, okay, is basically what we're looking at here. They're going to essentially work each other out and leave the ratio the same. So it turns out, even though you have increased velocity, you have increased distance to cover, which keeps the period the same. So it turns out you don't have to control the mass and the amplitude. It should not have any effect on your period. All right, but again, if you do a real experiment, you want to keep all things the same and only test one thing at a time. So there you go. So that's basically it. So simple harmonic motion. Make sure you know the difference between frequency and period, and then what will affect the pendulum, which would be length and gravity, which is why we have our one new formula here. Okay, 2 pi times the square root of L over G underneath the square root. And that's basically it. All right. Thank you very much.